Hi everyone! We're going to jump right into it and start talking about vectors and the geometry of space, but specifically we need to learn about the three-dimensional coordinate system. So the 3D coordinate system, it's going to build on what you already know about the two-dimensional system, but then just one extra dimension. So 2D, if you were to graph points or plot a function, you would have an x-axis, a y-axis, and then you would have ordered pairs to find points in this plane. So if I found a point like this, it's because I knew that there was an x and a y to locate that point. So now, three-dimensional coordinate system, we still have an x and a y axis, but now we have a third one, which is the z axis. So here's one way to kind of draw it. It is going to be a little hard to visualize because of our abilities to be able to see three-dimensional objects, but in a 2D space like this whiteboard. Okay, so just try to use your imagination and kind of visualize this having some depth to it, like popping out of the board and going back into the wall. So this right here would be our positive x-axis. Over here would be our positive y-axis. The x-axis is kind of coming out of the board, so is the y, and then the z-axis, which is the new one, is going up and down. So these are all the positive axes. They do have their negative values. If I were to go like back like this would be negative y. Toward like the inside of the board would be negative x, and then down here would be negative z. So this is our three-dimensional coordinate system. Points are found very similarly. If I locate a point in space, it's because I know its x value, its y value, and now its z value. If you want to plot points three-dimensionally, one way to do it is to use like rectangles. So Cartesian is also called rectangular, the coordinate system. So if I wanted to locate this point, the way I could actually do that is I would go over on my x-axis, whatever my x number is, okay, and then I would kind of mark that. I'd go on my y-axis, whatever y value that is, and I'd start to form like a rectangle here. Okay, I don't think my drawing is going to line up with my point. I'm finding a different point. Alright, and then my y or z value, let's kind of line this up a little better. Okay, maybe this might line up. So then my z value, I would mark it here, and then I would kind of go up from that intersection, and that's how I would get my point. So this is a different point than the first one I drew. And it's a little hard to see. I'm going to show you an image on the computer right now, just so you can kind of get a feel for what this is talking about. So here's our three-dimensional coordinate system. Notice the x-axis is here in red, the y-axis is the green, and then blue is our z-axis. So this is sort of tilted forward so that you can see all three axes, but if I were to move this and make it parallel with the xy plane, then you would just see like a two-dimensional system with z going up and down, and then x and y left and right. So if you can also go like this and just see the xy plane. So let me plot a point. I'm going to plot the point 1, 2, 3. And so watch what happens if I just kind of rotate this view. It looks like the point 1, 2 in the xy plane. And then when I show you the height on the point, or the z value, it has a z value of 3, so it's up here. But then the way that we see it is we normally tilt this forward. So you kind of have to use your imagination for how high up this actually is going to go. So it is parallel with 3 on the z-axis. So this coordinate system is considered a right-handed coordinate system, and this is different than if you were to call it a left-handed coordinate system, and I'll explain just what this means. So this is a right-handed coordinate system, and this is just letting you know when you're dealing with the positive axes. So here's how this works. If I were to place my right hand to where my fingers are on the positive x-axis, and use your imagination here because I can't actually put my hand over the z-axis, but imagine my right hand was kind of curled around z, but my fingers were on positive x. If I curl my fingers toward positive y, then my thumb points toward positive z. And that's all that this means. A right-handed coordinate system is just letting you know how to get the positive axes. Left-handed coordinate system would actually put my positive z down that way. So that's just why we call it a right-handed coordinate system. Now there are planes in this 3D coordinate system. So back when you were doing two-dimensional graphing, this was one plane. Now this system has an infinite amount of planes. Think of planes like a sheet of paper. So I can stack sheets of paper all throughout this 3D system. So there's three very important planes, and let me give those to you right now. So these are called the coordinate planes. And so we have the XY plane, and the XY plane has the equation z equals 0. Okay, so each plane in 3D has an equation. This is just a very nice equation, z equals 0. And so what that looks like, if you keep with this same like visualization, let me just kind of redraw it really quick. X, Y, Z is going up. Okay, this part right here, I'm going to highlight it in, let's go green. This part here, again, try to use your imagination for 3D. This would be the XY plane. It's like a sheet of paper that would cover all of the x-axis, all the y-axis, but your z value would be stuck at 0, so it's not going to move up or down. It's just this space right here. Okay, that is the XY plane. So there's two more, and you'll probably figure it out maybe already or right after I show you the next one, how to get all three of these. So the next one is going to be the YZ plane. Okay, so if you want to take a guess, the equation for that is x equals 0. So if I quickly redraw my coordinate system here, okay, and let's draw some negative axes. Okay, remember you're trying to visualize this being three-dimensional. Then the YZ plane, let's go ahead and use blue this time. Let me just label this for you. This was the y-axis, this was the z-axis. The YZ plane would be like a sheet of paper like this, parallel to the y-axis here. Sorry, my marker's running out. Okay, and that would be the YZ plane. A little hard to see, but hopefully you can kind of intuitively guess what's happening there. But it's where x is stuck at x value of 0, and then it covers all the y and z values, but x is only 0. And then the third one, hopefully you can guess it by now, XY plane, YZ plane, XZ plane. And so what's the equation for that? Well, you got it, y equals 0. Okay, and so see if you can visualize this, and I'll just draw my quick coordinate system here. And so if I were to visualize the XZ plane, y is stuck at 0, so x is here, z is there. It looks something like this, like my sheet of paper parallel to the x-axis there, and so it's kind of stuck right there at y is 0. So computer imagery might be a good way to intuitively build your ideas with this, and then eventually these drawings you'll be like, oh, okay, I know what she was trying to draw. So I apologize for my drawings, but hopefully you'll understand this idea of a three-dimensional coordinate system. So in this coordinate system, just one thing to mention is that your coordinate planes actually cut your system up into 8 spaces, and we call them octants. So if you remember, maybe in trigonometry you dealt with quadrants a lot in your graphing of points and things like that. So now, because there's 8 of them, we call them octants instead of quadrants. So you actually have like 8 distinct spaces. Now what we're going to talk about next is the distance between points in 3D space. If you remember the distance formula from algebra for two-dimensional space, you're good to go, because it's just an extension of that. If you don't remember, that's okay. I'm going to remind you right now. It does come from the Pythagorean theorem. Green doesn't want to erase. Okay, got it. So it's just an extension of the Pythagorean theorem. And so the distance formula for you, distance, and this is going to be between 2 points. This is in 3D space. I'm going to call the points just P1, P sub 1, which is going to have the coordinates x sub 1, y sub 1, z sub 1. And then my second point, I'll call it P sub 2, and it's going to have coordinates x sub 2, y sub 2, z sub 2. Okay, this is just generalizing two random points. That's what this notation is saying. So the distance between these 2 points is denoted like this. So first, the notation. The notation looks like absolute value bars because that actually is just representative of distance. And what's inside is just P1, P2. Okay, letting me know it's a distance between these points. Notation. You're not multiplying or anything, it's just notation. And so the distance formula would be if you were to take the square root of the hypotenuse of the triangle from Pythagorean theorem. You don't have to remember all that. Here's the formula. So square root of, it's going to be the distance between the coordinates. You're going to square them and then add those sums. So, or add them up. So we have the distance between the x coordinates, so x2 minus x1 squared. Then we start adding. Okay, the distance between the y coordinates, so y2 minus y1 squared. And then last, z2 minus z1 squared. Okay, so it's just the square root of the sum of the squares of the distances between the coordinates. No, it's a mouthful, but how far apart are the x's, how far apart are the y's, how far apart are the z's, get those numbers, square them all and add them, and then lastly take your square root. So let's try this out. I want us to find, so example, find the distance from the origin, I'll pick a nice point for one of our points, the origin is the nice point, to, let's go with a point 2, 3, 4. So what I'm going to do is I'm actually going to plot this point first, just so you can kind of visually see what's happening here, and then we'll find the distance. Okay, so our point in space, I'm going to use my rectangles to plot it. Let me just draw my axes real quick. I'll make a few tick marks so this plotting will be a little bit more meaningful. So let me place some tick marks on the x-axis, on the y-axis, and on the z-axis. Okay, and let's try to plot this point by hand. So I'm going to go 2 in the x direction, positive 2 is here. Let me make myself a little mark. 3 in the y direction, which is here. And let me find where those two would meet. Okay, that's not my point because I haven't considered the z value yet. So now I have to go up to z is 4. This part's the trickiest part to me because I have to kind of remember that this system is not parallel really with my eyes. It's leaning kind of forward so I can see the axes. So here's why I'm saying that. I'm not going to go all the way up to 4 up here. I kind of have to think that my system is tilted forward. So 4 is going to look a little lower. So I'm going to go up to a z value of 4. So kind of like that. There's a tilt to our system here. So all of that to get to this point. And so the question is, how far is that point from here? So what is that distance is what we're trying to figure out. So we can do it very quickly. Go right into our distance formula. And so the distance from this point to the origin, I'm just going to put d for distance in this case. And I have square root of, and I'll write this out, but you can kind of skip this step just because one of our points is the origin. But here's the work for it. The distance between the x values, so 2 from our one point and 0 from the other one, plus, so square that and then plus the distance from the y values, so 3 minus 0, square that, plus the distance of the z values, 4 minus 0 squared. Okay. Because the origin in 3 dimensions is just 0, 0, 0. So that's what I was saying. You can kind of skip this step because when you subtract 0, it doesn't look any different. It doesn't change anything. So you could just go right here. You could say 2 squared plus 3 squared plus 4 squared. And you want to give an exact value. So don't estimate this with a calculator. Just find an exact value. You can get an estimate for an additional answer, like an approximate, but also know that your exact answer is the one that's more accurate. So this is going to be plus 16, and for a final answer of square root 29. Alright, so the distance between the origin and that point is square root 29. So the next thing I actually want to show you about is the standard equation of a sphere. Okay, so you are now in 3 dimensions. So instead of dealing with circles, we are now dealing with spheres. Think of like a ball. So there is a standard equation for that. 2 things you need to know though. You need to know the radius and where your sphere is centered. So in general, I'm saying it's centered at x naught, y naught, z naught, and it has a radius of r. So these would be numbers for an actual situation, but this is in general. And so if you remember the equation of a circle, this might look very familiar, just with an added z component. So this equation is x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. Okay, so this is standard form of a sphere. You subtract where you are centered at in each of these quantities, and then you square the radius on the other side of the equal sign. So let's take a look at an example. I'm going to give you one here where you don't actually see this standard form, but the question that I'm going to ask you, you're going to need this standard form. So what I want you to do is to find the center and radius, center and radius of the sphere, and here is your sphere, x squared plus y squared plus z squared plus 3x minus 4z plus 1 equals 0. Okay, what's the center and radius? Well, the way it looks right now, no idea. So in order to answer this question, I actually have to go right back here. I need to write this equation in standard form. Once it's in standard form, then I can just look and I can see the center and the radius. So that's my main thing here. I have to find standard form. And so this is going to bring you back to your algebra skills. You must do something called completing the square. I hope that sounds familiar. I'm going to walk you through it though if you forgot how to do it. So we're going to complete the square right here. Let me just give us some room. Now, you have to complete the square a number of times. You actually have to do it for the x's, the y's, and the z's. So the very first thing I'm going to do here is actually rearrange this. So I'm going to put the x's next to each other. So x squared plus 3x, okay, let me just mark off what I found, are used. Then plus y squared, okay, then plus z squared minus 4z. And then I know I want my radius on the other side, so I'm just going to go ahead and say equals -1. Subtract that 1 over. And so what this is going to let me do is kind of focus on each variable one at a time. So I'm going to say I need to complete the square on the x terms, so I'm going to add the missing piece. When you're completing the square, it's currently incomplete. That's why you're finding the missing piece. So I'm going to add the missing piece. Now, notice the y doesn't have any other y's with it, so that one I get to just leave that one alone. Then the z's, I have a z squared minus 4z, and I have to add the missing piece for z. Okay, now think about it. Can you just add anything you want to an equation and it stay the same? No, unless you add it to both sides of the equal sign. Okay, so as long as I add whatever to the left also to the right side, we're good. Okay, so I'm going to find the missing piece. Let's go ahead and do the x terms. We have, let me remind you how to find the missing piece, 3 as our coefficient on our linear term. I know that sounds like a lot, but it's not really. Just look for the single variable like x or z, the one without the exponent other than 1. Look for the number in front, the coefficient. That's what you're looking for, okay? So take half of that. So you want half of 3, and then you square it. So you take half of 3, oops, let's write it like this. 1/2 times 3 squared, and that is the missing piece. This is always going to be the case. So that's going to be 3/2, not a very nice number to work with, but we're okay. Squared, which is 9/4. So I'm going to go ahead and put this in purple. 9/4 there, and to keep this equation balanced, 9/4 there. Let's go ahead and work on the z's. So I want half of the coefficient on the linear term squared. So that's going to be -4 squared. Half of that squared. So that's going to be -2 squared, which is +4. So we're going to add 4 to both sides of this equation. All right, the hard part's over, finding the missing piece. Not really hard, but you just have to remember how to find it. This is my goal. So if you remember with completing the square, the whole point of it is to get to a perfect square, something squared. So now the whole reason you added these missing pieces was to factor, which is what we're wanting for the standard form. So right here, we are going to factor, okay, we're going to factor this as something squared. The y was already nice and ready to go, so y squared is there. And then over here, the z's, this trinomial right here, is also going to factor as something squared. All right, now I'm going to start with the z's, because that one you might see just by looking. How does this factor? Well, this is actually going to be z minus 2 quantity squared. You can FOIL it out and check just to make sure. Over here now, you could think about it for a minute. You could say, okay, what multiplies to 9/4, but it adds to 3? But here's a shortcut. If you never learned this, I hope you remember it now. If you know it, that's good. Anytime you use completing the square, right before you square the missing piece, that number always goes in your factor. So it's x plus 3/2. And if you don't believe me, FOIL this out. You will get 3x and then a plus 9/4 when you FOIL. Okay, so these are now perfect squares. They have been factored. They were perfect squares up here, but now they're the factored form of it. And I just need to make that right side look a little better. Let's get a common denominator. So this is -4/4. This one's going to still be 9/4, and that's going to be 16/4. So that's, let's see, 25 minus 4. That's going to be 21/4. Not a very nice number, but that's okay. So now we're pretty much done as long as we answer the question. The question was, what was the center and the radius? And we know by looking. So the center, be careful, the standard form had minus signs. So it was x minus the x coordinate. So right here, the center is -3/2 for x. Because of standard form, it was x minus, if it helps you, write it with like a minus sign, minus a -3/2. Okay, that's how you would get back to standard form right there. The y value, notice it's just y squared, so there's really a -0 there. So that's the y coordinate. And then it's after the minus sign, that's going to go into the center, so it's +2. It's always after the minus sign that goes into our center coordinate. And then the radius is this quantity, but this is the radius squared, so square root that. You're going to get square root 21/2. Okay, real quick, square root 21, I don't know, officially it's irrational without a calculator, and so square root of 4 was 2. That's where that came from. Alright, now one's answered. Let me show you one more thing with this, just in case you come across the situation where you don't have a nice sphere equation where there's no coefficients on the squared terms. Let me explain. So this one was kind of nice, and here's why I'm saying that. You'll see the difference with this next one. So let me show you this one real quick. I won't go through the whole thing, but I just want to make sure you understand and remember what you know about completing the square. It only works if the coefficients on the squared terms are 1. So on this example, you actually have to factor out the 5. So this is going to be x squared plus y squared plus z squared. And then if I factor out a 5 from here, notice there's no 5s to begin with. So actually I'm dividing by 5. So this is plus 1/5 x plus 1/5 y. Oops. 1/5 y plus 1/5 z, and then the 4 is okay. It's on the other side of the equal sign. Go ahead and leave that. And so I won't go through the whole thing, but let me just show you at least one. If I focus on, let's say, x, I have my x squared, my 1/5 x, plus the missing piece. Okay, go ahead and just say dot 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 there. Then I'm going to put equals plus that missing piece, because remember, keep your equation balanced. So 2 things to mention here. When I find the missing piece, it's always going to be after I've factored out anything like this. So it's going to be half of 1/5 squared. Okay, so half of 1/5 squared, that's going to be 1/10 squared, which is 1/100th. Now, when you add this to the other side of the equal sign, you have to account for the fact that you factored. You factored out this 5, and so if I were to recognize that I added something right now, the 1/100th, that was never there before, if I were to multiply this all back together, this 5 would actually multiply this. And so what I really added that was never there, and what I have to balance, is 5 times 1/100th. So 5 100ths, or you could say 1/20th. So I just wanted to show you that just to remind you how that works. So the last thing I want to show you from this section about the 3-dimensional coordinate system is just a few examples of how to graph and how to visualize it based on what is given to you as functions or just equations of 3-dimensional space. So let me just do a handful of examples for you here. So let's graph x equals 5, comma, y equals 6. And remember, it's in 3-dimensional space. Okay? So I'm going to draw my coordinate system here. Let's see, z, x, y, and feel free to draw this all the way down and all the way back. Okay, and let me go ahead and kind of place my tick marks for these values. So I got to go at least to 5 on my x-axis, at least to 6 on the y, and I don't know anything about z. Okay, so let's figure out what that actually means. And so when I draw this, let's go purple. X is 5 is here, okay, y is 6 is here. Let's put these two together. Okay, now if I mark it as a single point, think about what that point would be. It would look like 5, comma, 6, comma, what? Well, notice where I placed it. I didn't go up or down, so it's actually when z is 0. So that is actually not this, because this doesn't tell me z is 0. So if it doesn't tell me z is 0, z can be anything. So if you want, you can say z equals z. Like z can be anything. So this is one single point. X is 5, y is 6 is also if I move up 1. Also if I move down 1. Also if I move up 2. So what this actually looks like is this is a line parallel to the z-axis, and that is this graph. Okay, so I know it's hard to see a little bit. It's not on the z-axis, it's actually like outward toward you more, but parallel to the z-axis. Every z value is valid for this equation, for this graph. Alright, let's try another one. How about x squared plus z squared equals 81 and comma y equals 7. Alright, let's start with this one. What does this look like? I'll give you a hint. Pretend this was a y. X squared plus y squared equals something. That's an equation of a circle. So this is an equation of a circle just in the xz plane. So equation of a circle, this is the radius squared. Okay, so quick reminder, I'll show you right here. From 2D space, you learned this equation for a circle. Okay, this is centered at the origin, by the way. So if it was centered somewhere else, it would look just like what we worked on for a sphere, but this is just in 2D. Alright, so just reminding you of what you know about circles. There it is. So this is a circle in the xz plane with radius 9. Then we'll address this. So let's go ahead and draw what we know so far. Alright, so I have my z, my x, and let's make this dashed. y was there. Okay, and so our center again is at the origin because we don't see anything getting subtracted from our x and y or x and z squared quantities. So then I have the x z plane, and I have a circle in that space, and the radius is 9. So this is 9 squared. So let me make a tick mark. I'm just going to kind of estimate this is where 9 would be on my x-axis. And the circle goes all the way around, so this might be where negative 9 is. On my z-axis, let's say that this is positive 9, and down here is negative 9. And so my circle, it's going to look a little lopsided from my drawing, but it looks like something like this. Alright, so it has a radius everywhere from the origin of 9. Now, if this y equals 7 was not there, here's what this would look like. It wouldn't be restricted to y is 0. It wouldn't be restricted to right here. So if y equals 7 was not there, it would actually look like a cylinder, kind of picture like a can of soup, sideways. Okay, it would look like this. It would be a cylinder. Now, so let me kind of draw that more, kind of like that. Okay. Now, when y is 7, that's one specific y value. I know my picture's getting kind of convoluted, but y is 7, let's just place it right there. It's a slice out of this can, out of this cylinder. So it's still a circle, but it's specifically at y is 7. So the red is this graph. Alright, a little hard to see, but just kind of do it in pieces, and then you'll get the idea. Let's try another one. Okay, the next one, I'm going to use some inequalities. Okay, so this next one, we're going to go with x is less than or equal to 0, y is greater than or equal to 0, and z equals 0. Okay? Alright, let's see what that's talking about. I'll draw my positive z, positive x, positive y. Let's get some negatives in there. And let's see what this means. Let's line that up a little better. Okay. X is negative. X is less than 0. Okay, well here's the positive x. So negative x is back there. So everywhere toward like the back is this. So I'm just going to kind of scribble it in because it's an inequality. Anything that makes this true is valid, so I have to take all of it. So anything back here, to include if I were to like make this higher and lower, it's like a three-dimensional thing. It's all back here. Okay, everything back there. High and low of all that. That's this part. Now, z equals 0, we'll do that last. Y is greater than or equal to 0. Let's go red on that one. So y is positive this way, forward. Okay, so that's over here and over here, and then everything above and below as well. Now, z equals 0 is the xy plane. So now I kind of have to erase some stuff and just keep where all of this lines up. And so you take a minute and kind of visualize it. It's back over here where x is negative, up here where y is positive, but only the sliced xy plane. And so it's really just this area right in here. Okay, so I'm going to erase some of this. Okay, we don't want that. Okay, that didn't work for the y is positive. We're going to erase some of this because this was not, x was negative, and we don't want anything lower or above z equals 0, so we don't want any of this. And that's it. So it's just this piece right here, and it'll make way more sense if I draw it for you back in 2D, because this is two-dimensional since z is 0. So in 2D, it would look just like this. Here's the x-axis, the y-axis. X is negative. Let's go ahead and put this in green. X is negative to the left. Y is positive up. It would be right here. Okay, this space. All right. Let's see. I think that's a good start for you to understand a three-dimensional coordinate system, and we'll just continue on from here and get into vectors pretty soon. So that's it for now.